I'm Andrew Jackson. I'm the economic geologist with Global Resource Investments, and I'm responsible for technical evaluations of the mineral companies and their properties that Global invests in. I put together this Ore Deposits 101 series of talks to help non-technical people understand ore deposits. The talks highlight some of the features of the main deposit types that investors in the resource sector may come across, and provide an introduction to the jargon that you'll find in press releases put out by exploration and mining companies. This is the sixth talk in the Ore Deposits 101 series, and it's devoted to Carlin gold deposits. Explorationists frequently talk about being in elephant country, meaning in good hunting grounds for big deposits. Historically, Carlin deposits are big elephants, but until recently, they were largely known to occur only in the limited hunting ground of northern Nevada. That limitation is now beginning to change. Let's start where we always do in this series, showing how Carlin deposits fit into the overall scheme of things. You'll remember that nature concentrates the metals by a process of partially melting crustal rocks at depth, letting them melterize through the crust and on the way cool, dumping valueless minerals such as feldspars and amphiboles, and then concentrating the useful minerals and metals in the remaining magma or hydrothermal fluid. Cool, dump the dull stuff, and skim off the useful materials. Carlin deposits are named after the little settlement of Carlin in northeastern Nevada, which is situated on the line of deposits that make up the Carlin Trend, where this type of deposit was first identified, and where the majority of the gold currently mined in the US is derived from. Current thinking is that the Carlin deposits formed at relatively shallow depths, maybe a little bit deeper than epithermal deposits, but not much. This is an outline of what we'll cover today. I'll start by defining a Carlin type deposit, and then giving some background into the history of Carlin deposits. Then I'll make a bit of a detour, and I'm going to paint a quick picture of how the western part of North America came into being, or how the West was made. This will help you understand how Carlin deposits formed, and set the stage for understanding how we go about exploring for them. Then I'll run through a few typical Carlin type deposits to illustrate their salient features, and finish up as usual with a list of points that I hope you'll take away with you. What makes it a Carlin deposit? There's some confusion sometimes about what defines Carlin-style deposits. Some geologists refer to them as sediment-hosted gold deposits, and include almost any gold deposit hosted in sedimentary rocks in this grouping. However, I think that most geologists prefer a tighter definition. Here are some of the characteristics that define Carlin-style mineralization. It's hosted in dirty carbonate rocks. When we refer to a dirty carbonate, we mean a limestone that has a significant clay content, and you'll see later why this is important. The gold in Carlin deposits is extremely fine-grained, often just a few microns across, and it's usually enclosed within pyrite or iron sulfide. If the ore is oxidized, then pyrite becomes hematite. And again, you will see why this is important when we talk about the history of Carlin deposits later in this talk. Arsenic sulfides, particularly orange orpiment and red realgar, are commonly associated with the mineralization. Black carbon and jasperoid or red-brown silica are also common, but silver and base metals are rare. These are essentially gold-only deposits. Where are Carlin deposits found? If you'd asked me this question a couple of years ago, my answer would have been virtually only in northern Nevada. There wasn't a similar occurrence in Argentina and some deposits in China that have been classified as Carlin deposits, but none of the ones that I have seen there truly fitted the requirements. What has changed in the last couple of years is the discovery of what is almost certainly Carlin-type mineralization in the Yukon. ATAC's Osiris and Conrad targets seem to fit all the requirements to be classified as Carlin-type deposits. How extensive and widespread the Yukon deposits will turn out to be will not be known for many years yet, but I think it's still fairly safe to say that the vast majority of Carlin deposits occur in northern Nevada, which is why I earlier referred to them as being big elephants, but within a limited hunting ground. Not only are they mostly restricted to northern Nevada, but the majority of the Carlin deposits are constrained to two narrow sub-parallel corridors, the Carlin Trend and the Cortez or Battle Mountain Eureka Trend. You can see these highlighted in the digital elevation map. The known Carlin deposits are marked as magenta circles, the size reflecting the size of their resources. As you can see, there are a couple of smaller trends and other single deposits scattered around the northern part of the state, but the recognized trends are key. They are the source of much of the 90 million ounces that have been produced from Carlin deposits to date. Carlin deposits have an interesting history because the first one of this deposit group was discovered only in 1961, in spite of northern Nevada having been crisscrossed by prospectors for over 100 years. Why was this? Well, the prospectors found the younger epithermal veins, but they relied on panning gold as a prospecting method. The fact that gold grains only a few microns across are invisible to the naked eye, and often even float in water, meant that the old-time prospectors walked right over the Carlin deposits. After Newmont discovered the original Carlin deposit in 1961, there was a long period when only the heap-leachable oxide ores were mined. The sulfide ore is refractory and expensive to treat, and it was only in 1986 that Barracks took the plunge and drilled some deep holes under their post pit and recognized the depth extent and higher-grade sulfide ores. Only then did they gain the confidence to go after these primary deposits. It was a pivotal decision. As I said, the total Carlin production to date is 90 million ounces. That's about 4% of the world production and more than 75% of the current US production. So what is it about Carlin deposits that makes them so attractive? Firstly, Carlin deposits can be very big. Goldstrike has over 14 million ounces of gold in production and reserves. Cortez Hills has reserves of nearly 15 million ounces. The primary sulfide ore can also be very high grade, and grades of several ounces per ton are regularly intersected in drilling. Secondly, shallow ore is usually oxidized, and it is simple and cheap to extract the gold in oxide ores. Thirdly, because of their size, they can often be mined by open pit without prohibitive stripping ratios. Open pit mining costs a fraction of underground mining, but as deposits get deeper, we can expect to see more and more mining of Carlin deposits from underground. Due to a combination of these factors, the economic cutoff for Carlin deposits has been low, often less than 0.2 of a gram per ton of gold in oxide pits. The final reason why Carlin deposits are so attractive is that both Nevada and the Yukon are politically stable. Although the ever-increasing legislative pressure on exploration and mining is a major impediment in Nevada. I'm going to change gears a bit here and step away from the deposits to give some background on how Nevada and the western half of North America was formed. We will cover some 3 billion years of history in just 15 minutes. And we start with the formation of one of the oldest continental crusts in the world, an Archean granite greenstone craton that formed between 3.4 and 2.7 billion years ago. Following that, there was a long period, almost 50% of the Earth's entire history, that does not really concern us too much. Under the influence of plate tectonics, All sorts of stuff happened during this period. Continents clumped together and split apart and then rejoined again to form the supercontinent of Rodinia. Volcanics and sediments were deposited over the Archean crust that was destined to become Western North America, but by 650 MA, geologists usually abbreviate million years to MA, by 650 MA, most of these cover rocks had been eroded, at least from what was to become Nevada. At 650 MA, the supercontinent split again, with Australia and Antarctica being torn off North America along pre-existing faults, and the Pacific Ocean opened up along the west coast of North America. We will now focus on the last billion years, or 25% of Earth's history. At 1 billion, or 350 MA before Australia and Antarctica were torn away, most of Nevada was below sea level. California didn't even exist, and significant dry land only began in Utah. Keep an eye on the grey lines showing the outlines of the future west coast of North America and the state of Nevada as we step through time. The time is shown at the bottom of the screen. Now fast forward to 600 MA. The Pacific Ocean has begun to open, and Australia and Antarctica have sailed away into the sunset. California is represented by just a few fragments of Antarctica that broke off during the rifting event and were left behind. Most of Nevada is still well below sea level, and sediments are accumulating on the new sea floor. The edge of the North American continent is marked as a yellow line running north-south through the center of Nevada, with shallow water continental shelf to the east of the yellow line and deeper oceanic basin to the west. This new continental margin plays an important role in the genesis of the Carlin Deposits. By 500 MA, on the shallow water continental shelf, where there's enough light available for corals to survive, thick layers of limestones and dolomites with varying amounts of clay are being deposited. Off the shelf to the west in deeper water, only muds and fine-grained sands are accumulating, the products of erosion of the continental fragments and the mainland. If we were to draw an east-west cross-section across the red line, it would look something like this. The section is vertically exaggerated for clarity. You can see the pink Archean crust joining the new formed green oceanic crust and overlain by the early buff-colored sediments that were laid down during and immediately after the rifting that formed the Pacific Ocean. The limestones are forming on the shelf, and deep-water mudstones to the west. There's a transitional shelf edge zone where the two fingers facies interfinger. By 425 MA, the topography along the coast over present-day Colorado and Utah has been eroded down and redeposited as thick mudstones offshore. However, this quiet period is about to end, as a new subduction zone forms out in the Pacific Ocean. Oceanic crust begins to be pulled eastwards and slipping under the North American continent. And riding on this plate of oceanic crust is a volcanic arc that is rapidly approaching the continent. By 370 MA, the volcanic arc has reached the edge of the continental shelf, bulldozing the deep-water mudstones ahead of it, folding and contorting them as it goes. This is the beginning of the so-called Antler Orogeny, which plays an important role in the tectonics of Nevada. If we go back to our cartoon east-west section again, the process looks like this. The volcanic arc is approaching from the left, bulldozing the deep water sediments ahead of it, and pushing those deep water sediments up the continental slope and onto the continental shelf. The pressure from the shelf causes the old extensional faults that formed when the continent is ripped apart to invert or reverse direction. Sediments continue to be pushed eastward across the shallow shelf, riding on a thrust fault known as the Roberts Mountain Thrust. The deep water sediments above the thrust are collectively known as the upper plate, while the carbonate and transitional rocks below the thrust are known as lower plate rocks. The pile rises above sea level and starts to erode, dumping coarse sediments, known as the overlap sequence, in front of it. The upper plate subsequently overrides this overlap sequence. Okay, back to the pterodactyl's view of our evolving coastline. By 340 MA, those deep water sediments that are being pushed onto the shelf produce a new mountain chain that has broken surface to form an elongated island that is now being eroded. This new mountain chain straddles modern-day Nevada and the area of the Carlin and Cortez gold corridors. The Roberts Mountain thrust breaches the sea floor along the eastern margin of those abducted deep-water sediments. The continental shelf to the east of the thrust sags due to the weight of the sediment, and the coastline retreats eastward, with extensive limestones continuing to form in the warm and shallow seas. By 300 MA, the strain of the oceanic plate, due to the pushing of the mass of deep-water sediments over the shelf, causes the oceanic plate to break, well to the west of the bulldozed sediments, and subduction continues along this new break, sliding at a very flat angle under the shelf to the coast and beyond, under Utah. Concurrently, on the east coast of North America, the North Atlantic Ocean closes, and Europe slams into the east coast, forming the Appalachian Mountains. The compression from both the east and the west causes the center of North America to buckle, pushing up the ancestral Rocky Mountains. This is what the process looked like along our east-west section across California, Nevada, and Utah. You can see the new slab of oceanic material subducting under the continent. The oceanic slab continues to disappear down the subduction zone and into the mantle. The sediments and volcanic arcs that have been deposited on the ocean floor are being scraped off the plate and piled on top of the upper plate sediments. These new piles of debris slide on newly developed thrust faults, similar to the Roberts Mountain thrust. And they move the wedge of sedimentary material eastward over the continent and well into Utah. By 170 MA, continued eastward subduction of the Pacific Ocean plate causes more volcanic arcs to collide with the continent. This Nevada orogeny results in another phase of thrusting across Nevada. By this time, the subducting Pacific Ocean plate has lifted almost all of Nevada well above sea level. And by 150 MA, the whole of Nevada and western Utah form part of an extensive high plateau. The ocean to the east in the center of the continent has disappeared altogether, to reveal sandy and muddy sediments that had accumulated from the erosion of the ancestral Rocky Mountains. At 65 MA, eastward subduction is still continuing, and compression and thrusting and crustal thickening continue over Nevada and Utah. The subducting plate melts as it slides under the continent. Resulting magma rises up through the crust to form an extensive intrusions and volcanic activity along the west coast of North America. The massive granites of the Sierra Nevada mountains form as the core of this magmatic event. The flat subducting plate continues to force its way eastward under the continent, and the volcanic arc follows just behind its eastward advancing edge. By 55 MA, the eastern edge has reached halfway across Colorado, raising the Rocky Mountains in the so-called Laramide orogeny. When the eastern edge of the plate reaches where Denver now stands, the spreading ridge of the oceanic plate is subducted, and subduction of the Pacific plate abruptly halts. After 320 million years of being under continuous compression from the repeated collisions of volcanic arcs rafted in on the Pacific Plate, North America suddenly goes quiet. Thrusting has stopped, subduction and the related volcanic activity have ceased, and placid lakes begin to form in sags over Utah. But this period of quiescence does not last long. Beneath the continent, the relatively cool slab of subducted oceanic crust that has insulated the overlying Nevada from the heat of the mantle is rapidly approaching melting point. At about 42 MA, this heat shield burns through, and the hot mantle is once again in direct contact with the lower crust. All hell is about to break loose, and the Carlin deposits are about to come into being. You can see that subducted oceanic plate melting and exposing the lower crust to the heat of the mantle. For the last 600 plus million years, the western US crust has been constantly thickened, firstly by thousands of meters of sediments being deposited on the shelf and oceanic floor, and then for the last 320 million years, thrusting has doubled the thickness of the sediments seen huge volumes of intrusives introduced. Because the crust has been under compression, this buildup has been sustainable, with the base of the crust sinking into the underlying mantle. If you watched my introductory talk in this series, you may remember this slide, showing how the relatively light continental crust floats on top of the denser mantle, like a raft on water. Load more people on top, and the raft simply displaces an equivalent weight of water and keeps on floating, albeit just a little bit lower. In Nevada, the underlying raft of continental crust that has been protected by the cool underlying oceanic slab is suddenly exposed to the very hot mantle, and this blast of heat causes the base of the crust that has supported the high plateau of Nevada to rapidly melt. The strong foundation that the sedimentary pile was built on suddenly loses its strength, and like cheese placed on top of a hot hamburger, a large portion of the southwestern US simply collapses, relaxing along the original faults and spreading westwards away from the center of the continent. Here you can see the lower crust partially melting, and the original faults and thrusts, both steep and shallowly dipping, going into extension. This process began at approximately 42 MA. The partial melt from the base of the crust is enriched in gold in the same way as the partial melt described in my talk on greenstone belt deposits. And because it's hotter and less dense in the crust above it, the melt rises through the crust, taking advantage of the old faults that are being remobilized. As the pressure drops, the aqueous fluids separate out and rise ahead of the melt. Closer still to the surface, the gases exhale from the fluids, forming a hot and acid vapor that rapidly spreads ahead of the rising fluid, permeating even the finest cracks and intergranular spaces. When these hot acid vapors reach the limestones, they attack the calcite, dissolving it in a similar way to antacid tablets dissolving in water. But remember that these limestones are not pure, clean calcite. They're made up of a mix of grains of calcite, dolomite, and clay. Whereas the calcite readily dissolves in the dilute acid, the dolomite and clay do not. What is left after the calcite is gone is a porous lattice of dolomite and clay. This lattice partially collapses under the weight of the overlying rock, but it still remains porous when the gold-bearing neutral pH fluids catch up, and the fluids can readily pass through this newly created sponge. Secondary result of this hot vapor and fluids is that any oil that is trapped in the oil reservoirs tends to get cooked and turned to carbon. Black carbon is a very common feature in Carlin-type gold deposits. The neutral pH fluids begin to deposit quartz and pyrite in the pores of the altered rock. The early fluids contain little gold, But late in the process, there's a pulse of fluid that is highly enriched in arsenic and gold. The gold drops out of the solution along with the arsenic, forming a rim around the earlier formed pyrite grains. Then the gold is exhausted and only arsenic is deposited as the system cools and wanes, depositing red realgar and yellow orpiment. Although the gold pulse is very short-lived, it is responsible for the vast majority of the gold mined in Nevada. This is probably a good time to talk briefly about how the gold is extracted from Carlin ores. If the ore has been subjected to weathering, the pyrite is oxidized to porous hematite, and cyanide solutions used in extraction can come into contact with the fine gold and dissolve it. Oxide ores can be easily treated with standard carbon and pulp mill circuits, or even heap leached. This makes extraction cheap and simple, a big advantage of a shallow weathered ore deposit. However, if the ore has not been weathered, the gold is locked up in the pyrite grains, which then have to be oxidized artificially to break down the pyrite to hematite. This is usually done by roasting or using an autoclave, which is basically an industrial scale pressure cooker. It's well-proven technology, but expensive in terms both of initial capital and operating costs. In addition, the presence of carbon in the ore is a complication. When the gold is released from the pyrite and dissolved by the cyanide, it tends to bind with the carbon and you're back to square one. Sulfide ores with carbon are sometimes referred to as being doubly refractory and require the addition of a reagent to prevent the gold from binding to the carbon. As the mineralizing fluids rise up the feeder faults through the sedimentary layers, they bleed out into those layers that are particularly porous and reactive. Carlin deposits are sometimes described as being Christmas tree shaped, and stacked ore horizons are common. Exploration therefore requires an understanding of both the local structure and the stratigraphy. So that is a quick outline of how Carlin deposits formed. But it's not quite the end of the story. As the collapse of the Nevada crust continued after the deposits were formed, and in fact extension is still continuing today, 40 million years later. The existing faults and a whole series of new faults continued to move, both displacing and breaking up the ore deposits. In addition, the faulting formed a series of mountain ranges, separated by sinking valleys, the so-called basin and range topography. Erosion removed parts of the mountain ranges and deposited the debris in the adjacent valleys, in places burying the host rocks under up to 20,000 feet of gravels. This obviously makes exploration highly challenging. Now let's turn to exploration for the Carlin deposits. This is the image that I showed earlier of the topography of northern Nevada with the location of Carlin deposits marked. Note how most of the deposits that have been discovered to date are either in the ranges or clustered along the edges of the flat-bottomed valleys where gravel cover is thin. Exploration for Carlin deposits occurred in a number of phases. Early exploration focused on areas where the favorable lower plate carbonate rocks outcropped at surface and sulfide mineralization had been completely oxidized. The next phase of exploration focused on deeper sulfide portions of known deposits. Then the explorers stepped out to look under shallow cover of upper plate or younger gravels. But now most of the low-hanging fruit have been picked, and we're entering an even more challenging phase where the exploration is turning to blind deposits under deep gravels and upper plate rocks. This is where the next group of deposits are likely to be found. But the bar is much higher for these given the cost of deep exploration drilling and the need for higher gold grades that will support deeper underground mining and completely unoxidized ores. During the first phase of Carlin exploration in the 1970s, much exploration was simply grid drilling 30-meter RC holes along outcropping structures. Such holes cost less than $1,000 each. Today's exploration, however, requires 1,000-meter diamond drill holes that cost $250,000 a pop, and it doesn't take many of those to exhaust a junior explorer's finances. But fortunately, since those early days, we've learned to be much smarter and more surgical in our exploration. And future exploration will require an even better understanding of both the genesis and the controls of mineralization. Cartoon on this slide illustrates the main features of Carlin deposits. They tend to form on old faults that have been reactivated during extension. They are usually associated with anticlines that formed during the earlier compression, particularly those that formed above thrust faults. Dirty limestone units provide the best hosts, and they are often spatially associated earlier intrusives that fractured the host rocks, allowing the fluids to penetrate more widely. So how can we use a knowledge of these controls to design exploration programs? Well, let's look at the faults first. And one way we can do it is to learn to recognize the old faults with the longest history of movement, as those are the ones that are likely to provide deep tapping channelways for the mineralizing fluids. But with the myriad of faults crisscrossing an area, how do we recognize which are the old faults as opposed to the younger ones which may be irrelevant to the story? Well, there are several ways, and here's a cartoon section of a fault that was actively moving during sedimentation and long before mineralization came in. And we can identify these old faults by the presence of linear limestone reef material along the fault edge, or the existence of changes of sedimentary stratigraphy, such as a change in thickness of sedimentary unit across the fault, or by the presence of exhalative barite or exhalative sulfides, or even sedimentary breccias along the fault. Recognizing any of these features while mapping can help differentiate these old faults that we are really interested in. But sometimes the critical feeder fault in the lower plate may be completely hidden by the overthrust upper plate rocks. So how can we detect these hidden lower faults? Well, the old fault in the lower plate, when it is reactivated during thrusting, tends to form a step, and this will tend to trip up the upper plate as it's pushed over it, warping the fold axes. So changes in the orientation of fold hinges in the upper plate rocks may therefore indicate the presence of potential feeder faults hidden in the lower plate rocks. Geochemistry can also be used to detect leakage from blind ore deposits. This geochemistry can detect trace levels of gold or arsenic or evidence of oxidizing sulfides. And the sample mediums that are collected can include soils or soil gas or even vegetation. The most successful soil gas technique looks for changes in the ratio of oxygen to carbon dioxide, caused by buried oxidizing sulfides absorbing the oxygen and as a byproduct producing acid that attacks the limestone to produce carbon dioxide. So the image on the right hand side there shows a plan over a known deposit, and it shows the enrichment of CO2 relative to oxygen. In vegetation sampling, vegetation such as sagebrush can trap the metals from the groundwater that it absorbs. Collecting sagebrush samples on a grid and reducing them to ash and then assaying that ash has been used to identify buried mineralization in certain cases. Geophysics also plays a valuable role in Carlin exploration. Magnetics can be used to identify hidden faults and intrusives. Gravity can identify shallow gravel cover in the valleys and hidden displacements of the lower plate rocks, and hence possibly feeder faults along the edge of those displacements. It can also detect decalcification in limestones caused by the acidic gases that accompanied and foreran the mineralizing fluids. Seismic surveys can see displacements along hidden faults, as well as anticlinal fluid traps and favorable host horizons. So if we were to summarize the top targeting criteria, they'd look something like this. We should be focusing our exploration in the Carlin or Cortez corridors, within 500 meters of long-lived inverted crustal scale faults, usually within a kilometer vertically of the Roberts Mountain thrust and usually below it rather than above in the lower plate rocks, in other words, within a kilometer of Eocene intrusions and possibly even older Cretaceous intrusions, in fault-related hanging wall sediment anticlines, and these may display abundant black carbon, and in dirty carbonate host rock, usually but not always in the lower plates, showing decalcification, i.e. a gravity low. There will undoubtedly be some Carlin deposits that don't have all these features, but the majority of the deposits will exhibit most of them. The last part of this talk is a quick run through a couple of actual Carlin deposits to give an idea of their characteristics. We'll begin with Barracks Goldstrike deposit. It's in the north of the Carlin Trend. Goldstrike is the mother and father of Carlin deposits and is responsible for Barrick being the biggest gold producer in the world today. As you can see, the geology exhibits a number of our targeting criteria. It's hosted in dirty carbonate rocks in the lower plate located just under the Roberts Mountain thrust. It's in an anticline in the hanging wall of the post fault, an old fault that can be demonstrated to have been active during sedimentation 500 million years before the mineralization was introduced. It's also next to pre-existing intrusive that probably played a major role in structurally preparing the rocks for mineralizing fluids. Goldstrike is just one of a cluster of deposits in this part of the Carlin Trend. The deposit, as I said, is a monster, and it produced 1.2 million ounces in 2010 alone, and at a production cost of $410 an ounce. So far, more than 35 million ounces have been extracted, and there are still another 12.6 million ounces in reserves remaining. However, as with most sulfide operations in the Carlin Trend, the ore is refractory and it requires roasting or autoclave oxidation to release the gold. The second example is Barracks Cortez Hills deposit, which was discovered by Placidome in 2002 and went into production in 2010, producing ore from both open pit and underground. It is on the Cortez Trend, as opposed to the Carlin Trend, towards the south of that line of deposits. This is a view of the deposit looking to the southwest, very early on in the exploration program. It was completely blind, buried under tens of meters of valley-filled gravel. The deposit is likely to end up containing more than 15 million ounces of gold. The location of Cortez Hills was identified by applying the targeting criteria described earlier. The deposit lies adjacent to the Cortez Fault, which began life as an extensional fault during the early sedimentation. It was then inverted into a thrust fault during the Antler Orogeny, and finally remobilized as an extensional fault again during the mineralization phase. The thrusting resulted in the formation of an anticlinal fold in the hanging wall of the fault, which provides an ideal trap for the mineralizing fluids. That anticline strikes northwest, rotated 45 degrees from the normal north-south folding trend. Also during the Antler Orogeny, a large intrusive was in place nearby, which helped with ground preparation. So I guess the discovery of the Cortez Hills allows us some confidence in the validity of the exploration model. This is a cutaway diagram looking towards the east, showing the low-grade mineralization in drill holes near surface, and the deeper, shallowly plunging high-grade zone that is being mined from underground. The Pediment Deposit is a shallow deposit also related to the Cortez Fault. This is a recent photo of the new Cortez Hills open pit looking towards the northwest. As I said earlier, virtually all Carlin deposits discovered to date are located in north-central Nevada. However, in 2010, ATAC Resources discovered gold mineralization in the Yukon that has all the hallmarks of a Carlin-style mineralization. This is the discovery location. ATAC's Nadaline mineralization is located in an anticline in the hanging wall of a regional scale fault. It's hosted by dirty limestones, and the gold is very fine and associated with pyrite, orpiment and realgar. We don't yet know the age of the mineralization, but I would not be surprised to learn that it is of a similar age to the Nevada mineralization, and associated with extensional faulting that occurred at the end of a long period of compression. So the hunting ground for Carlin deposits may have been dramatically expanded now. I'll end this talk with one summary slide of the main points you should remember on Carlin deposits, the takeaway points. Carlin deposits are very attractive to major mining companies, as they can be very big, and they're often high grade as well. They are indeed big elephants. They're hosted in dirty limestones. In Nevada this means mainly in the lower plate rocks, and associated with long-lived crustal scale faults. The gold itself is too fine to see with the naked eye or to pan. It is the so-called micron gold. Carlin deposits can often be mined by open pit, although this is less likely in the future, and that means cheap mining and a low cutoff grade. Oxidized deposits usually have simple metallurgy and therefore cheap extraction. Sulfide ore, on the other hand, is often refractory. There are no significant economic byproducts from Carlin deposits. Most Carlin deposits discovered to date occur in northern Nevada, although there are deposits in Mexico, China and Argentina described as Carlin type. The recent discovery of unequivocal Carlin-style mineralization in the Yukon throws open a whole new area for exploration. However, it's too early to be able to say whether any of this Yukon mineralization will prove to be economic. And finally, Carlin deposits are not common, and the easy ones have already been discovered. There is still only a relatively limited hunting ground, and Carlin deposits are indeed wily elephants. I hope this video will help your understanding when you're reviewing exploration news releases about Carlin deposits. The next talk that I am preparing in the Ore Deposits 101 series will cover the volcanogenic massive sulfides, or VMS deposits, the product of those black smokers that develop on the seafloor.